There is something about falling that you already understand, and something about it that no one understands at all. And the strange part is that both of those things are true at the same time. Think of the last time you dropped something. A cup off a counter, a phone off a couch. For a fraction of a second, before your hand could react, the object simply fell, obeying a rule so old and so familiar that you never think about it. A rule that has been running quietly in the background of every motion you have ever made. Gravity pulls, objects fall, and the world resumes. It is the most unremarkable event imaginable. And yet, if you follow that same simple act of falling far enough, if you take it and push it past oceans, past mountains, past the Earth itself, past stars and past galaxies, you arrive at a place where falling stops being simple. You arrive at a place where falling becomes the strangest, most violent, most reality-bending event the universe is capable of producing. You arrive at the edge of a black hole.
That is the paradox sitting at the center of everything we're about to explore. Falling is the most ordinary motion there is, and yet somewhere out there, falling is also the process by which time itself appears to stop, where space folds in on itself, where the laws of physics as we know them quietly hand in their resignation. Something that feels like nothing, a simple downward motion, becomes something that current physics cannot fully describe. That is the promise of what follows. We are going to take the most familiar experience in the world and follow it until it breaks. Before we go further, if you are new here, welcome. Settle in, get comfortable, and if this kind of question interests you, consider subscribing, because today we are going to follow this particular question as far as it will take us, past the point where most explanations stop, and into the place where physicists themselves admit they are no longer certain. Part 1. Let's begin with what you can actually imagine, because that is where every real understanding has to start. Picture a spacecraft approaching a black hole. Not a cartoon vortex, not a swirling drain in space, but an actual region of extraordinarily curved space-time, born from a star that once shone for millions of years before running out of fuel and collapsing under its own weight into something almost incomprehensibly dense. As the spacecraft gets closer, at first, nothing seems unusual. Gravity is gravity. It pulls, just as it always has, just as it pulled that cup off your counter. But then, something starts to change, subtly. And the strangeness has nothing to do with the ship itself. It has to do with the relationship between the ship and everyone watching it from a safe distance. To an outside observer, watching through a telescope from a comfortable, uneventful distance, the ship appears to slow down. Not because its engines fail, not because it hits resistance, but because the very fabric it is traveling through is changing. As the ship approaches the boundary of the black hole, the point of no return that scientists call the event horizon, the light it emits takes longer and longer to climb back out of the gravitational well. Each second the ship experiences seems to stretch from the outside into minutes, then hours, then something that from a distant vantage point never technically finishes. The observer will watch the ship approach that boundary forever, slowing infinitely, fading infinitely, without ever quite seeing it cross.
But here is the detail that changes everything.
From the perspective of the astronaut inside the ship, none of that stretching happens. Their clock ticks normally. Their coffee cools normally. Time, to them, feels exactly as it always has. They cross the event horizon in an ordinary, unremarkable moment, one instant among many, and they may not even be able to pinpoint exactly when they did it. Two observers, one event, two completely different experiences of when or even whether it happened. That is not a flaw in our instruments. That is a real property of how time behaves near enormous gravity, and it is the first sign that our intuitions about a single, universal now do not survive contact with a black hole. But this is still just the surface. The problem gets stranger as we move to the next scale. Part 2. Now consider what is actually happening to the geometry of space itself, because falling into a black hole is not simply falling through territory the way you might fall through air. It is falling through a landscape that is actively rearranging itself as you move through it.
But here is the detail that changes everything. From the perspective of the astronaut inside the ship, none of that stretching happens. Their clock ticks normally, their coffee cools normally. Time to them feels exactly as it always has. They cross the event horizon in an ordinary, unremarkable moment, one instant among many, and they may not even be able to pinpoint exactly when they did it. Two observers, one event, two completely different experiences of when or even whether it happened. That is not a flaw in our instruments. That is a real property of how time behaves near enormous gravity. And it is the first sign that our intuitions about a single, universal now do not survive contact with a black hole. But this is still just the surface. The problem gets stranger as we move to the next scale. Part 2. Now consider what is actually happening to the geometry of space itself. Because falling into a black hole is not simply falling through territory the way you might fall through air. It is falling through a landscape that is actively rearranging itself as you move through it.
Space and time, according to general relativity, are not a fixed stage on which events happen. They are a single, flexible fabric, one that bends in response to mass and energy, the same way a heavy object placed on a stretched sheet creates a dip that other objects roll toward. A star curves the fabric of space-time gently. A black hole curves it so extremely that the geometry near its center stops resembling anything found in ordinary experience. As an object approaches the event horizon, the curvature intensifies to the point where the paths available to it start to funnel in only one direction, forward, always forward, toward the center. Past the event horizon, this is the detail that quietly undoes the mind. The roles of space and time appear to swap. Outside a black hole, you can choose to move left, right, forward, back, but time only moves one direction, toward the future. Inside, according to the mathematics, that structure inverts. Moving toward the singularity, the theoretical point of infinite density believed to sit at the black hole's core, becomes as unavoidable as moving forward in time is out here. You cannot choose to pause. You cannot choose to turn around. Falling is no longer optional. It is not even really a direction anymore. It is closer to a countdown. This is the part almost no one expects when they first hear about black holes. It is not a destination you steer toward. It is a future you cannot avoid. In exactly the same helpless way you cannot avoid next Tuesday.
Consider for a moment how strange this actually is compared to every other kind of falling you have ever experienced. When you drop a cup, gravity pulls it down, but you could, in principle, catch it. You could redirect it. The cup falling and the hand reaching are both events happening within a shared, ordinary structure of space. where multiple outcomes remain available right up until the moment of impact. Near a black hole, that shared structure itself is what changes. It is not that the astronaut becomes weaker or that their engines become insufficient. It is that the destinations available to them narrow, layer by layer, until only one remains. Physicists describe this using what are called light cones, the set of all possible paths light, and therefore any signal or object, could take from a given point in space-time. Far from a black hole, these cones point in every direction, tilted only slightly by gravity, the way a chart of possible futures might slope gently downhill. Near the event horizon, the cones begin to tilt so sharply that they point almost entirely inward. At the horizon itself, one edge of the cone points straight down, toward the center, permanently. Past that point, every cone, without exception, points only one way. There is no tilt left to exploit, no clever trajectory, no burst of thrust powerful enough to reverse it, because reversing it would require moving backward through what has effectively become the flow of time itself.
Only this explanation creates its own problem. If falling toward the center becomes as inevitable as the passage of time, then what exactly is waiting at the end of that fall? Part 3. To understand what waits at the center, we have to widen the frame from a single black hole to the wider population of these objects scattered across galaxies. Because the ones we know the most about are not the exotic, microscopic ones some theories imagine. They are the extraordinarily massive ones, some carrying the mass of billions of suns, sitting silently at the hearts of galaxies, including our own. At the center of the Milky Way sits a black hole with a mass several million times that of our sun, an object whose event horizon is wider than our sun, and yet compact enough to hide comfortably inside the orbit of Mercury, and yet it is nearly invisible, betrayed only by the frantic orbits of stars whipping around empty space at speeds that make no sense unless something enormous and dark is anchoring them. We do not see black holes directly. We see their gravitational fingerprints, the way they choreograph the motion of everything nearby, the way they bend starlight passing behind them, the way matter spiraling toward them heats to millions of degrees and screams out X-rays before vanishing. Every black hole we have ever detected has been found this way, not by looking at it, but by watching the universe behave as though something is there that light cannot escape.
And that detail, light cannot escape, is worth sitting with for a moment, because it means a black hole is not merely dark the way a shadow is dark. It is a region of space where the very fabric of causality has curved so sharply that light itself, the fastest and most fundamental messenger in the universe, cannot outrun the pull. If light cannot leave, nothing can. Not radio waves, not gravity's own ripples, not information of any kind. The event horizon is not a wall. It is a one-way membrane stitched into the geometry of the universe itself. It is worth pausing on just how strange this method of discovery really is. In 2019, an international collaboration of researchers linking radio telescopes across the planet into a single instrument the size of the Earth itself produced the first direct image of a black hole's shadow, the dark silhouette cast against the glowing, superheated matter spiraling just outside its boundary. What that image showed was not the black hole itself, since a black hole by definition emits nothing to see, but the sharp-edged absence it leaves behind, a void outlined in fire. It was, in a very real sense, a photograph of a boundary rather than a photograph of an object, evidence not of what is there, but of the precise place where our ability to observe simply ends. But this raises a much deeper problem, one that widens far beyond astrophysics and into the foundations of physics as a whole.
Here is where the anomaly appears, the place where our understanding runs up against its own limits. If nothing, not even information, can escape a black hole, then what happens to everything that falls in? Every atom, every photon, every scrap of physical information describing an object that crosses the event horizon, according to one of the most trusted principles in all of physics, should never simply disappear. Physicists call this the conservation of information, the idea that the universe, at its most fundamental level, keeps a kind of perfect ledger. Nothing is ever truly destroyed, only rearranged, only transformed, always in principle recoverable if you had detailed enough knowledge of a system. Burn a book, and in theory, if you could track every photon of light and every particle of ash and smoke with impossible precision, you could reconstruct every word that had ever been written on its pages. The information does not vanish, it only becomes exquisitely hidden. Black holes appear at first to defy this rule. When a black hole slowly evaporates, a process theorized by Stephen Hawking involving faint radiation leaking out over unimaginable timescales, that radiation looked, in Hawking's original calculation, featureless and thermal, carrying no trace of everything that originally fell in. It was as though a library burned down, and the smoke curling into the sky carried no imprint of a single sentence from a single book.
That apparent contradiction between a law insisting information is never destroyed and a calculation suggesting a black hole quietly erases it is what physicists came to call the black hole information paradox. And for decades, it sat unresolved at the center of theoretical physics, occupying some of the sharpest minds of the last half-century. What is worth being careful about here is where that problem actually stands today, because the picture has shifted. Over roughly the last decade, theoretical work has led most physicists to conclude that the information is very likely preserved after all, that Hawking's original calculation was incomplete, rather than a genuine violation of nature's bookkeeping. In that sense, the paradox in its starkest form is widely considered closer to resolved than it once was. But, and this is the honest frontier, exactly how the information escapes, what that implies about the interior of a black hole, and whether it can be reconciled cleanly with an astronaut falling smoothly through the horizon, remains genuinely contested. The ledger, most now believe, balances. The mechanism by which it balances is still being argued over. That is a strange thing to sit with. An object we can detect, whose gravity we can measure with extraordinary precision, whose shadow astronomers have literally photographed, and yet whose deepest interior behavior remains a place where the best minds in physics still disagree about the details. But even this is not the deepest layer. To understand why the paradox exists at all, we need to descend one level further, into the collision between two of physics' greatest theories. Part 5. This is where the intuition breaking becomes unavoidable, because the black hole information paradox exists precisely at the seam where general relativity, our theory of gravity and large-scale structure, meets quantum mechanics, our theory of particles and probability. And these two frameworks, individually spectacular, do not yet fit together cleanly. General relativity describes the smooth, continuous curvature of spacetime, the graceful bending that produces orbits, tides, and the paths of falling spacecraft. Quantum mechanics describes a jittery, probabilistic world of particles that do not have definite positions until measured, that can exist in strange, overlapping states, that behave according to rules with no clean analog in ordinary experience. At the scale of planets and stars, both theories work beautifully, each in its own domain. But at the singularity, the theoretical point believed to exist at a black hole's core, where, according to general relativity's equations, density and the curvature of spacetime climb toward infinity,
general relativity is pushed into a regime where quantum effects can no longer be ignored, and on its own, it stops producing sensible answers. Infinite density is not a physical description. It is a signal, a flashing warning light telling physicists that the theory has been pushed past the domain where it is valid. The same way a calculator returning an error is not evidence of infinity, it is evidence you have asked it a question it cannot answer.
This is where intuition fails hardest. It is tempting to imagine the singularity as a physical object, a tiny, impossibly dense dot sitting at the center like a marble. But most physicists suspect that is not what is actually there. It is more accurate to say that our current description of nature simply stops making predictions past that point. The way a map stops being useful past its edge, not because the territory ends, but because the map makers never charted it. What is actually happening at the core of a black hole may require a theory that does not yet exist, a full theory of quantum gravity, something that would successfully merge the smooth geometry of relativity with the probabilistic granularity of quantum mechanics. Several candidate frameworks exist, string theory and loop quantum gravity among the most discussed, but none has been experimentally confirmed, and each remains, honestly, speculative. To understand why merging these two theories is so difficult, it helps to see what each one insists on, at its core, that the other cannot easily accommodate. General relativity treats space-time as smooth and continuous, a fabric with no smallest unit, capable of being divided infinitely without ever hitting a floor. Quantum mechanics, by contrast, insists that at sufficiently small scales, nature becomes grainy, discrete, built from the smallest possible units of energy, and many physicists suspect, potentially of space and time themselves.
A theory that treats space-time as infinitely smooth and a theory that treats energy as fundamentally granular are at their foundations telling two different stories about the basic nature of reality, and a singularity is the one place in the universe where both stories are forced to describe the same point simultaneously. It is less like two maps disagreeing about a border, and more like two entirely different languages being asked to describe the same sentence, with no dictionary yet built to translate between them. And this is the part that quietly reframes everything we thought we understood about falling. The ordinary act of falling, the same act that pulled a cup off your counter, becomes, at sufficient scale, a direct route into the one region of the universe where our best physics admits it does not have a final answer. Only, even this framing does not close the loop, because there is a further possibility, one that pushes the entire question into stranger territory still. Consider the strongest, boldest version of the open question, the frontier where genuine hypothesis lives, and where nothing here should be mistaken for settled fact. Some physicists have proposed that what we call a singularity may not be a point of infinite density at all, but rather a boundary beyond which our current equations simply cannot see, perhaps concealing something entirely different, a region of extremely dense but finite matter, a bounce leading to a new expanding region of space-time, or, in some of the more speculative proposals, a kind of gateway to another region of space and time altogether, sometimes described loosely and imprecisely by the public as a doorway to another universe.
It is important to be honest about where this stands. This idea, sometimes called a black hole cosmology or a bounce scenario, is an active area of theoretical exploration, not an established result. There is no observational evidence confirming it, and many physicists consider it one possibility among several, not the leading one. What can be said with more confidence is only this: nothing rules it out yet, and the honest answer to what lies at the very center of a black hole remains, at the time of this recording, unresolved by both theory and observation. And if that possibility turned out to be correct, even partially, then the original question we started with, what happens when you fall into a black hole, was never really about a spacecraft or an astronaut, or even about black holes specifically. It would be a question about whether an ending is ever truly an ending, or whether every apparent conclusion in the universe is secretly a transformation wearing the costume of a stop. This is the layer where the question stops being purely scientific and starts becoming something closer to philosophical, because it forces a specific and uncomfortable reconsideration. Perhaps disappearance and transformation are not opposites at all. Perhaps what looks from the outside like the total erasure of an object, an astronaut, a spacecraft, a star, is simply the limit of what our current vantage point is capable of witnessing. The same way the ship crossing the event horizon never technically finishes crossing it. From far enough away, forever.
It would be natural to stop here. This is the point where the story feels finished, where we could return to the cup falling off the counter and call the circle complete. We have followed the most mundane motion imaginable to a place where two clocks disagree about when something happened, where forward and downward become the same unavoidable direction, where a law of nature was nearly overturned before being narrowly rescued, and where the smoothest theory we have of gravity meets the strangest theory we have of matter, and produces not an answer, but a boundary. That would be an ending. But the strange thing about this particular subject is that its endings keep turning out to be thresholds, and there are two more we have not yet crossed. Before we close, though, it is worth lingering a little longer on what actually happens to the astronaut themselves, because this is where the physics stops being abstract and becomes, briefly, almost unbearably personal. For a black hole with the mass of a star, the tidal forces near the center become so extreme that the difference in gravity between an astronaut's head and their feet would stretch them apart long before they ever reached the singularity, an effect physicists, with a rare flash of dark humor, actually call spaghettification. But for the truly massive black holes, the ones sitting at the centers of galaxies, the math tells a stranger story. Because these black holes are so large, their event horizons sit so far from the crushing central point that the tidal forces right at the boundary are, surprisingly, gentle. An astronaut could cross the event horizon of a supermassive black hole and, for a while, notice nothing unusual at all. No violent stretching, no dramatic warning, just the ordinary hum of instruments, the ordinary weight of a body in freefall, the ordinary silence of space. They would have already crossed the one boundary in the universe that guarantees they can never send word of what they found back to anyone who has not crossed it too, and it would feel, for a while, like nothing had happened at all. That detail deserves a moment of stillness. The most consequential boundary in physics, a threshold that separates everything reachable from everything permanently unreachable, might not announce itself. There might be no flash, no resistance, no sensation of crossing over. You would only know, if you knew at all, by doing the math and realizing there was no longer any direction left that pointed back home. But this is still only the surface of the problem, because even this description, strange as it already is, still assumes we know what inside means in this context, and that assumption, examined closely, begins to give way. Now consider this. From the astronaut's own perspective, falling toward the singularity, standard general relativity predicts that they would reach it and experience its infinite tidal forces in a finite amount of their own personal time, perhaps only fractions of a second for a stellar mass black hole, slightly longer for a supermassive one. Their story, from their own point of view, has an ending, however violent. But from the perspective of the rest of the universe, watching from outside, that ending never arrives. The astronaut's final moments, stretched by the same time dilation we described earlier, would seem to smear out across the entire remaining lifespan of the black hole itself, fading rather than vanishing, until the black hole eventually evaporates through Hawking radiation, a process that for a supermassive black hole would take a span of time so long that comparing it to the current age of the universe would understate the difference by dozens of orders of magnitude. So we are left holding two different endings for the same person, occurring in the same event, and neither one is wrong. The astronaut's ending is fast, private, and final. The universe's version of that same ending is slow, public, and stretched across a timescale that dwarfs the age of everything that currently exists. This is not a contradiction physics has failed to resolve through carelessness. It is a genuine feature of how time and gravity interact, a feature suggesting that when something happens is not a single fact about the universe, but a relationship between an event and whoever is asking. And if this possibility is correct, then the question that opened this video, what happens when you fall into a black hole, never had a single answer, because the very idea of a single when may not exist. There is one final layer, and it connects the fate of a single falling object to the fate of everything. Black holes are not simply cosmic dead ends, obstacles, or curiosities scattered through galaxies. Current models of cosmology suggest that over spans of time, almost too large to meaningfully picture, longer than the current age of the universe by a margin that turns ordinary numbers meaningless, black holes may represent one of the final acts of cosmic history. Stars will eventually stop forming as the raw material for new ones is exhausted. Existing stars will burn out, one by one, over trillions of years. And many of the remnants they leave behind, especially the largest ones, will collapse further into black holes, or be swallowed by the ones already waiting in the dark centers of galaxies, over time spans that make the age of the universe so far look like a single tick of a clock. It has been proposed that black holes themselves may become the dominant objects remaining in an otherwise dark and diffuse cosmos, until even they, through the same slow Hawking radiation that would one day claim our hypothetical astronauts' remains, evaporate into faint whispers of radiation, and nothing else remains at all. If that is where the universe is headed, and this remains a projection built from current physics rather than a certainty, then falling into a black hole is not an exception to the rules governing the rest of the cosmos. It is a preview of them. Every star, every planet, every observer who has ever watched the sky may be participating in the same basic process, just on a radically different timescale. Matter falling, gathering, collapsing, and eventually dispersing into radiation that carries no obvious trace of what it once was. This brings us back to where we began, but the question has grown. We began with a cup falling off a counter, the most forgettable motion imaginable, and followed it until it led to disagreeing clocks, to a direction that stopped being optional, to a law of nature nearly broken and then narrowly preserved, to two theories of physics colliding without resolution, to a boundary that might not even announce its own crossing, and finally to the suggestion that this same quiet process, matter falling inward and eventually radiating outward into silence, might be the shape of the universe's own ending. Falling, it turns out, was never the simple thing it appeared to be. It was always a motion capable, under the right conditions, of testing the limits of time, of causality, of information, and of reality's own bookkeeping. The cup falling off your counter and the star collapsing into a black hole are, in the deepest sense available to physics, the same event, differing only in scale. And if that is true, then perhaps nothing that falls, anywhere, at any scale, ever really finishes falling. It simply crosses into a place where we can no longer watch, carrying with it a question about endings that the universe itself may still be in the process of answering.